Hi, I'm Professor Shalaev. I would like to welcome you to Birck Nanotechnology Center, where I serve as a scientific director for Nanophotonics. I'd like to mention that Birck Nanotechnology Center is a part of a bigger research thrust and activities here in Purdue. It actually belongs to the Discovery Park, which hosts many different multidisciplinary research areas. And we would like specifically talk about nanophotonics. We have a number of faculty members working in this exciting field. Let me introduce two of my colleagues representing nanophotonics, Professor Alexandra Boltasseva and Professor Alex Kildishev. And I hope you would share with us the excitement which we have working on various aspects of nanophotonics. Let me say a few words about plasmonics and metamaterials. Those are two things which actually enable nanophotonics. But let me first start with motivation with the whole field of nanophotonics. Probably it's one of the biggest challenges that we as a society face to process information faster. The quest for faster processing information is ever-standing problem which we need to address. And with the current nanoelectronics, of course, we have tremendous progress in terms of scaling down all the components and processing information quite fast, but still not fast enough. There are some fundamental limits such as RC delays, energy related, because of which you cannot actually process information faster than roughly 100 gigahertz, basically 10 to the 11 operations per second. And the way to speed it up further is actually to employ photons instead of electrons. Photons do not have mass, and they propagate at the ultimate speed, which is speed of light. In that sense, one could say that photons are ultimate unit of information. But the challenge is how to manipulate and control photons on nanoscale. And that's exactly where plasmonics comes at hand. Because plasmonic materials are materials that can confine light down to nanoscale. Plasmons are basically oscillations of clouds of free electrons, and they could be very confined, this oscillation, and that's the way to bring light down to nanoscale. When we speak of metamaterials, which typically include these plasmonic components, we imply materials which are artificially designed and engineered that have properties going beyond of those that one can attain with materials existing in nature. One could say that metamaterials is a material platform that enables nanophotonics, basically control manipulation of photons on nanoscale, with the ultimate goal to have as complex functionality which, as we have with electronics, and as small elements that control photons as we have in the case of electrons, but process all this information much faster. And that's the motivation behind of nanophotonics, and that also explains the interest, the tremendous interest and huge research activity in the area of plasmonics and metamaterials that enable nanophotonics and eventually would make it possible to process information much faster, to make our computers faster. Even though it's perhaps the most important applications, I should mention also other very important applications related to nanophotonics, such as energy conversion, solar thermophotovoltaics, biomedical applications, sensors with unique sensitivity, and data storage. There are many, many applications which nanophotonics can enable, and eventually you could have it all on a chip and process all the needed information at the ultimate speed as fast as possible. Yet another important development in that regard actually could be quantum photonics, when you employ unique properties of quantum physics based on quantum superposition, and that makes possible to process information even faster than you would do it with classical photonics.
Hi, I'm Alexandra Boltasseva, and my primary focus is research in optical materials. So the progress of our society has always been connected to advances in materials. So the society went from Stone Age to Bronze and Iron Age, Steel Age and Industrial Revolution. And today, with all our gadgets and smartphones, we are in a way harvesting the fruits of software and information revolution that had advances in pure silicon and pure silica glass in its heart. So in order to make the next technological leap, the area of nanophotonics needs new material platforms. And Plasmonics, as one of the most important avenues of nanophotonics, is in desperate need for finding out new constituent materials that could enable efficient, compact, durable devices that can be integrated with standards in semiconductor industry. The problem with Plasmonics nowadays is that current materials we are using, such as gold and silver, have some significant drawbacks. They absorb too much light, they are soft, they are incompatible with standards in semiconductor processing, and they are expensive.
By the way, do you remember how this idea of titanium nitride first came into our minds, why we started to think of this?
Of course. That's the way it's all started. We had this conference on a boat on a beautiful Russian river Volga, and we're stopping at those small towns with most beautiful churches. And then we realized, by discussing this with some of other team members, that domes of Russian churches nowadays are not made of gold, but they're covered by titanium nitride.
That's it.
But they're as beautiful as golden domes. So we thought if it looks like gold, it must have optical properties that are very similar to those of noble metals. And that's how we started to look into that.
That's the story.
So here at Purdue, we are investigating and researching the new types of plasmonic materials that could bring dramatic advances in many nanophotonic technologies. So we are looking at different classes of materials that are in a way not as metallic as noble metals. They are still plasmonic in the optical range, which means that we can get the functionality we want in our nanophotonics devices, such as focusing light down to nanoscale or providing very efficient local heating. However, those materials, and we call them intermetallics, are ceramic materials that are highly durable and highly robust. Another class of plasmonic materials that we can use is highly doped semiconductor oxides. So there are many classes of materials that can indeed replace metals in various plasmonics and optical metamaterial applications. And those materials do hold a great promise for practical devices in those areas. Due to their excellent optical properties, their durability, their contamination safety, their stability at very high temperatures, they can enable a next generation of devices that are very compact, that are compatible with standard in semiconductor industry, that are very durable, and can also operate in harsh environments where high pressure, contaminants, high temperatures are present, such as aerospace, gas, and oil industry.
Hello, I'm Alex Kildishev, and today we will talk a little bit about computational nanophotonics. Computational nanophotonics enables us to predict the real-life behavior of nanoscale photonic and optoelectronic devices in the real-life environment by using their equivalent numerical models. Computational nanophotonics can also address global numerical problems of computational multiphysics. With computational nanophotonics, we can take Maxwell's equations, quantum mechanics, heat transfer, fluid dynamics, combine that all together and solve this complex combination in one run. The applications of these techniques include the following. So on one hand, we can study and invent and discover new physics. On the other hand, with our techniques, we can design and optimize actual devices in actual real-life environment. Here I may refer to our modeling of optical black holes that can absorb sunlight at any angle. This feature is very useful for solar energy harvesting, for example. And another great example is multiphysics modeling of nanoscale lasers and single photon sources, which are very useful for quantum communication and quantum computing. And finally, our methods for design and optimization of near-eye stereo displays may revolutionize the augmented reality systems. Computational nanophotonics can help us to optimize and design new optical systems, discover new physics, and can help us to pave the way for new discoveries in the area of quantum nanophotonics and new emerging technologies.
One of the most central components to any computing device is its processor. At the heart of such components are millions of tiny devices called transistors, connected in vast arrays of circuits. In the past, transistors were continually improved by shrinking them, allowing them to operate faster and consume less power. However, continued scaling to improve their performance, size, and efficiency has resulted in devices with critical dimensions nearing the single atomic level, where conventional scaling is becoming extremely difficult. As a result, new technologies for integrated chips are being investigated, and one of the most promising solutions is optics. Optics is already a crucial technology for information transfer today, in large part because photons are the fastest things we know of in the universe, and they can carry our data at light speed, and we hope to bring this power on chip.
However, fitting light onto a chip is challenging, as the typical size of optical components is much larger than that of electronic components. In traditional photonics, we can squeeze light down to about its wavelength, but even that is 10 times larger than the size of an electronic transistor. To address this problem, our research focuses on using metallic optics and nanophotonics, which allows us to squeeze light to the smallest possible dimensions, which are comparable to that of electronic components. In this particular project, we have developed integrated nanophotonic devices which can guide and manipulate light using materials that are compatible with current microelectronics.
By designing chips with optical components, we are attempting to reduce the energy consumed by structures and increase the speed more than 100 times, all while making them lighter, more mobile, and more reliable.
Good afternoon. My name is Justus Undekifa. I'm a PhD candidate in the School of Electrical and Computer Engineering at Purdue University. My research concerns designing novel nanotwistors for trapping and manipulating very tiny objects. And these objects could be over 1,000 times smaller than the thickness of the human hair. Examples include particles on the size scale of viruses, for example. And when these kind of particles are suspended in solution, they typically diffuse very, very fast. And we would like to have a way to be able to hold them in place, trap them in place, so that we can analyze them. So the conventional nanotwistors, which can achieve high spatial resolution trapping of these kind of particles, are very slow. They rely on diffusion to load the trap, and this could take several tens of minutes or perhaps hours, depending on the concentration of the particle field system. So recently we introduced a novel design paradigm that now makes it possible to trap these particles within 2 seconds, for instance. And because of this, we can now grab particles in solution and be able to analyze them, and perhaps even design some novel biosensors out of these kind of devices. So one thing that really excites me most about this research is that from now on, thanks to our work, the younger generation of creative thinkers and innovators who end up working in this field in the future no longer have to wait for several tens of minutes or perhaps hours to get a particle trap. By simply following our design paradigm, they can get to target particles within a few seconds. And I think that's pretty important.
We are developing materials that are durable in harsh environments, and unlike conventional plasmonics, refractory materials retain their properties at high temperatures in aggressive chemistry and under high mechanical loads. Combining the refractory properties with high plasmonic response, these materials enable the use of plasmonic elements in the technology areas which are limited by material-related problems. Nanometa Technologies is a spin-off from the Nanophotonics group at Birck Nanotechnology Center and develops products for the fields of energy harvesting, high-temperature sensing, data recording, and photothermal therapy.
Our research on refractory plasmonics, it goes beyond engineering and aims to extend our understanding on the fundamental aspects of material science and radiation. In our lab, we develop the tools to probe the optical properties of these materials under harsh conditions, such as extremely high temperatures. So the durability of these materials will help the researchers, to get a deeper understanding in the fields of quantum plasmonics and near-field radiative heat transfer.
Nowadays, most of the information on the internet is transmitted by sending a light pulse in the optical fiber. The process of sending such a light pulse can be thought of as throwing the light packet from a sender to the receiver. If we carefully examine this light packet, we can see that it consists of billions of light particles, so-called photons.
The physical properties and behavior of a single photon are extraordinarily different from those of, say, light packets utilized in internet communication. This area of physics known as quantum optics is actually what gives us the tools and artillery necessary to study the single particle nature of light.
Our goal is to create new efficient single photon sources that could be conveniently used in today's technology. Actually, nanoscopic diamonds with dimensions about 1,000 times smaller than the thickness of a human hair can emit single photons. But they will do it relatively slowly and in all directions, causing many of these photons to be lost forever.
In our lab, we create medium or artificial materials, so-called metamaterials, which can improve the properties of these single photon sources. For example, the photon can be emitted faster and in specific direction.
Such single photon sources can help us create completely new tools for information processing and communication that are more secure and more efficient than the ones that are currently used.
Light is the ultimate physical quantity used to send information. It propagates with unmatched speed and provides the highest data rate. Yet when it comes to on-chip applications, it's more common to use electronic than optical systems. This is because optical elements cannot be scaled down to the size of electronic devices, which is an essential requirement for to integrate a large number of applications in a small device like a cell phone. Therefore, optical metasurfaces are developed to overcome these limitations. They can perform optical operations over a very small distance scale, like tens of nanometers, which is already compatible with electronic devices. They are also suitable for on-chip fabrication with the current silicon industrial techniques.
And a metasurface overcomes the size limitations of conventional optics through replacing natural materials with artificial nanostructured materials. And to manipulate visible light, a metasurface can comprise of elements that are as small as 1/10,000th of a single human hair. And to realize metasurface for a particular application, we require such high accuracy assembly of structures. And similar techniques of the silicon industry can be used to implement such metasurfaces. And a lot of optical elements, such as lenses, holograms, and spectrometers has already been demonstrated. And new applications are still emerging through integration of optical metasurface and electronic devices.
2D materials are a class of material that consist of only one or few layers of atoms arranged in two-dimensional sheets, visually similar to a stack of Post-its.
So the properties of a single layer or a few layers of atomic sheets are very different from their bulk counterparts. For example, graphene, which is a single layer of carbon atoms, can be peeled off from bulk graphite using this. So graphene has been known to interact with electromagnetic radiation all the way from microwave to ultraviolet light, like no other materials can, not even its parent bulk graphite.
That's right. And amazingly, it's not just graphene. There is a whole big family of 2D materials like transition metal dichalcogenides, MOS2, WSO2, etc. When they are few atomic layers thick, they show a vast variation of particularly unique properties and interesting physics. Those are related to the high degree of confinement of the carriers inside the body of few angstroms thick. Now, what we are doing in the lab using these materials is using them as light-absorbing elements, also placing them alongside specially designed photonic and plasmonic structures to improve the overall efficiency. For their atomically flat structures, it's very useful to integrate them in such on-chip devices and many other flat optical components.
Yes. To give an example, one project that we're currently working on involves designing a graphene-based broadband photodetector. We designed a special plasmonic structure to enhance the collection of incoming light onto graphene and enable graphene to convert the incoming light into electrons with a much higher efficiency than with graphene alone.
Here is one example of our numerical efforts to do simulations of these nanostructures. This is a randomly distributed civil nanowire networks used as transparent conducting electrodes. We developed a multi-scale model to handling this complexity. So we actually playing the piece puzzles in the nano world. We can see that if we divided this whole picture into small pieces and got the optical responses from each frame, we can see they all have these different optic responses. But if we average over them together, the magic happens. We can see a good match between the simulation results and the experiment measurements.
And hence, the computational nanophotonics allows us to simulate complex and very large random structures like that.
Hi, I'm Swati Paul. I'm a research scientist here in Professor Shalaev and Professor Boltasseva's lab. I'm also Outreach and Engagement Officer working at Birck Nanotechnology Center. Here, as a research scientist, I am developing nanomaterials for nanophotonics. As you know, that nanomaterials are not naturally occurring and they need to be synthesized in the lab. Different synthetic approaches tunes up the properties of these nanomaterials. Exactly this is what I'm trying to do. When you use different approaches to fabricate these nanomaterials, we are trying to see how the optical properties are changing. So I'm using the sonochemistry, reactions under atogenic pressure and elevated temperatures, as well as nitridation of oxide materials to synthesize these CMOS compatible materials such as titanium nitride, zirconium nitride, and also aluminum doped with zinc oxide, vanadium oxides, as well as tungsten and molybdenum chalcogenides. It is a nice experience and proud to work with the teammates in Professor Shalaev and Boltasseva's lab to study these materials. I am also extending this nanomaterial synthesis approach by collaborating with different faculties and well-known material scientists out of Birck Nano Center.
Until relatively recently, it was thought that all materials were linear. This means that their optical properties such as absorption, refraction, and reflection were independent of the light's intensity. However, following the invention of the laser, it was discovered that at very high intensities, the optical properties of the material were significantly different. In fact, at such high intensities, light can interact with itself, and the constituent particles of light, photons, can either combine together or split apart to form new photons at different energies. This is nonlinear optics. As optical and material scientists, we are looking for new ways to create and engineer materials which concentrate light into nanometer-sized volumes, thereby increasing the nonlinear interaction. Plasmonics and metamaterials are two ways to do just that.
So we study various metamaterial geometries and alternative plasmonic materials other than silver and gold to enhance these nonlinear interactions. For example, we study very thin metamaterials or metasurfaces that have a unique resonant behavior that can be used to enhance the conversion of light from one frequency to another. We also study thin films of alternative plasmonic materials that have a unique property in that their dielectric permittivity is very close to zero. And what this allows us to do is to have dynamic refractive index control, which allows for modulation of signals on chip. We also study engineered materials that have a unique dispersion or hyperbolic dispersion, which is not naturally found in optical materials. And we study these materials to see how they can enhance nonlinearities at the nanoscale.
In our nanolaser research, we are using a unique technique called Nanophotonics to create ultra-compact lasers at the nanometer scales. The secret behind this capability is that a metallic nanocavity is used here, which could provide extreme confinement of light through coupling between light and collective electron oscillations at the surface of metal. Our goal is to create ultra-compact lasers at atomic scales through advanced fabrication techniques and explore their potential applications.
We are combining top-down and bottom-up approaches to fabricate various artificial plasmonic structures, including one-dimensional, co-shear, and nanoroid-shaped particles, two-dimensional metasurfaces, and three-dimensional metamaterials. With these structures performed as optic cavities for lasing, we have developed several laser sources with controllable figure merits, such as we can control their emission efficiency, lasing threshold, and emission directionality, as well as lasing mode confinement.
We expect our nanolaser research will ultimately contribute to the future information community.
I hope you enjoyed this short video, and to sum up this presentation, let me just mention that in our nanophotonics research, we're trying to be technology driven and bring together the excitement of fundamental science and engineering, which eventually would enable real life applications.
I'm expecting that you have learned something today about exciting field of computational nanophotonics.
And please do visit us at Purdue and learn how Discovery Park seamlessly integrates various research with state-of-the-art facilities and industry partners.